Hello, good afternoon, everyone, and welcome back to distance learning again. So let's hope it's not going to be too long this time. Okay, so we're in this chapter about Lebesgue integration, and it's time to see more clearly all these important theorems that I told you about. So the first one we saw last time was called Beppo Levi, from the name of an Italian mathematician of the beginning of the century called Beppo Levi. And it's called the monotone convergence theorem in general, if you want to talk about that. Yeah, that's its general name. So what are we talking about? It's this idea where we want to be able to exchange the limit and the integral sign. So that gives you some conditions when you can say that the limit of the integral is equal to the integral of the limit. Okay, so the limit of what you are going to ask? The limit of a sequence of functions. So I've got something like this, a sequence of functions. So x, the argument of the function is a real value, and we've got an index n that tells you that we've got a sequence, so a sequence of function. This sequence of function, the assumptions are they are measurable. So for this, as I told you, we don't really have to worry about that. All the functions we're going to see are measurable. They have to be positive. So for any x, fn of x greater or equal to 0. Well, as you know, now we can use the almost everywhere abbreviation to say, well, it's everywhere except maybe on a set of null measure, and so that it's not going to be of any importance in terms of integration. So we have this sequence of functions, the assumption measurable, positive, increasing in n, that is for fixed value of x. We've got that fn of x is going to be smaller than fn plus 1 of x. Okay, we also have to have pointwise convergence almost everywhere. That means there exists a limit as n tends to infinity of the value f of the sequence fn of x. Okay, so as n tends to infinity, we have a pointwise limit for fixed value of x. This sequence fn of x is converging to f of x, so almost everywhere again. And of course, as this sequence is increasing, well, this f of x, this f function, this limit function is going to be the supremum of the sequence. Okay, then what do we have? We have a huge typo here, actually. We have, this should be an n. So please correct this. Okay, so conclusion of this theorem is that the limit of the integral of the sequence, so the limit as n tends to infinity of the integral, so the integral we mean is always by default on R, and we are not even going to write it because this is Lebesgue integral, doesn't let you, it's always on R, on the whole space. Is, well, which just means as we saw, well, this part just tells you that, well, it corresponds to the supremum. Well, this limit is equal to, as we said, the integral of the limit. And the integral of the limit is just simply the integral of f of x. Okay? And we saw this application in tutorial that you could very easily extend this theorem to series. So in that case, it means that you want to exchange integration and the sign sum. So the integral of the sum of the series, the integral of the limit series, is equal to the sum of the integrals. Okay, and we also saw that we could extend this definition to decreasing sequences. In that case, we would have, so what is it? We still have measurable positive functions. This time, the sequence is decreasing pointwise. So fk of x is greater or equal to fk plus 1 of x. And we'll still have convergence pointwise convergence almost everywhere. So as n tends to infinity, this sequence fn of x tends to a value f of x for almost all x's, and of course this time, as the sequence is decreasing, f is going to be the infimum of the sequence. Then we have integrability of f. If ever, well, you remember the proof, we build an auxiliary increasing sequence, which is made out of f1 minus fk, or my f1 minus f1 of x minus, so the first item of the sequence minus fn of x. That's going to be your auxiliary sequence, and if you consider this sequence, it's increasing, and we are in the same case as before, so that in the end it's going to converge. We will really have that the integral of f1 minus f, which is the limit on that side, is going to be equal to the limit as n tends to infinity of f1 minus fn. Okay, and in order to get the equality that we are looking for, meaning the integral of the limit of the integral of fn is equal to the integral of the limit, meaning integral of f. In order to get this, we absolutely need that to be bounded on both sides, otherwise it's we wouldn't be able to rule out this. Okay, all right, so this being said, we're going to go to the I would say the main theorem, which is actually an extension of the previous theorem, and it's called Lebesgue dominated convergence theorem. What do you do if you've got a sequence? Okay, so it's still the idea of getting a sequence. All right, so we still have fn of x is a sequence of real valued measurable function on a measure space. All right, so here you've got the full text of the theorem. Usually, I know I didn't spend time on that, but usually, as you remember, the fact that we can measure the space is important, and we must say how we measure it. So this is commonly a common notation to say we work on R. The way we measure the kind of sets we're looking at is called the Borelian sets, and you've got a description of what is a Borelian set at the beginning of the lecture notes. Mu is the notation that I used here for the Lebesgue measure. So you remember, for us, it's going to be very transparent. I mean, it's just going to be the size of the interval, and if you've got more complex sets, then you just do the size of disjoint, the sum of disjoint intervals. And if it's isolated, remember, if you're looking at isolated points, the measure is just 0. Okay, this being said, let's go back to the Lebesgue dominated convergence theorem. So we still have our sequence fn of x. We still have that the sequence converges pointwise almost everywhere to a function f. All right, but now we're not going to assume any kind of monotonicity. This sequence could be increasing or decreasing of whatever. The only thing that, well, the new thing, and it's going to be very important, is we are going to need a dominating function. A dominating function. Okay, so how do we say that? We assume that the sequence, items of the sequence, is dominated by some function g, such that for any n, for all n, that's important, the function fn of x is pointwise smaller or equal to some dominating function g. So the function g is dominating, and that for all or almost all x. Okay, then the conclusion is our function f of x is going to be integrable, and that, well, in other words, the limit of that is going to be 0, which also implies, well, what the kind of conclusion we had earlier. So that's how that's really the proof, the conclusion of the theorem that you have to remember. Again, we will be able to exchange limit and integration.